Okay, so good evening and yeah, good morning, I guess, for some. So this is our 10th webinar in this Game Theory and Network Theory webinar series from GamesNet. And today's speaker is one of the founding members of GamesNet, Professor Sudipta Sarangi. He is currently the department head and professor of economics at Virginia Tech. Sudipta's research interests lie in economic theory and its application to areas like experimental economics, networks, development economics. In 2020, he has received the Kuznets Prize for his research on the historical origins of gender inequality. He serves on the editorial boards of JEBO, Journal of Public Economic Theory, Economic Modeling, and Studies in Microeconomics. He is a research associate of DIW Berlin, Gate Institute of Leon Saint Etienne, and the Lima School of Economics. Previously, he has worked at the NSF and also was a distinguished professor of business administration at Louisiana State University. His book is, there's a book upcoming, The Economics of Small Things, will soon be published by Penguin India in November 2020. So that's that, and without further ado, I will hand over the stage to Sudipta. Sudipta, you have been doing this for last 9 lectures. So basically, you can do it whatever way you want. If you want me to have keep an eye on the chat box, I'll do that.
So thank you. Thank you, Anirban. Yes, keep an eye on the chat box. That is always useful. I want to, first of all, say greetings, and I hope everyone is doing well. Good morning, good afternoon, good evening. So normally I would not be speaking in the series, but we had a late withdrawal and we're not quite sure what to do. So instead of letting the week go blank, I decided to present something. And so obviously the problem was that I didn't really have a full paper ready to present. So I cobbled together 2 papers, one that is finished and one that is still work in progress. And so that's what I am going to do today. So discuss 2 papers, but they are related to one common agenda, which is that of simultaneous formation of, or thinking about the formation of multiple networks at the same time. So that's basically the overall agenda. And so with that, let me see if I can start the screen share. Okay. And so, and as I said, feel free to interrupt me with questions and so on. And let me get to full screen. Why does it not like? Oops. Yes. All right. So yeah, please, if you need, just put something in the chat box. I'll catch it, or Anirban will tell me, or I will stop at some points to see if there is a question. Okay. So with that, let's get started. So, typically networks define the interaction structure between agents. So that's basically how we think of a network, that it is what connects the agents. And the situations we want to think about here are the idea that usually agents are members of more than one network. So that's what we want to get to here. That's the question we want to solve, to see how we can understand the formation of multiple networks. So the first model is going to be about the formation of a network, where we will assume that one network is given and agents form the second network. And the question is, how does the structure of the first network affect the formation of the second network? But there is a second stage where agents utilize both networks. Okay, so they put both networks to use. So it's a 2-stage game. And so the formation of the second network depends on the structure of the first network, and including what will happen in the second network in terms of the effort. The second model I'm going to discuss, and I'm going to discuss this very briefly, and only one part of this, is what happens when agents are simultaneously forming both networks. So in some sense, we go from model 1 to model 2 with the idea that in model 2, we are still looking at, we drop the idea that one network is given, and we think about the simultaneous formation of both networks. Okay? And the inputs in this simultaneous formation will be degrees. All right. So now I'm going back to go to the first model where one network is given and then the other network is being formed. Now, those of you who are from India obviously know the story of marriage alliances between these large business communities, the Marwadis and the Parsis. There is a lot of marriage between families, and that creates business alliances, and that has been responsible for the rise of many of these business families. So this is the marriage alliance in details are not, but you can find reasonable evidence for this in a book by Damodaran called Caste and Business in India or something of that sort. Then, of course, there's the classic paper on the Medici by Ansel and Paget, which says that when Cosimo de' Medici came to power in Florence, he started to make a bunch of marriage alliances. And so as he put together marriage alliances, and the Medici became more and more central in the marriage network of Florence, they also became more and more important in the business network. So he simultaneously tracks the growth of the importance of the Medici, or the centrality of the Medici in the business network, in the marriage network, and how that makes them more and more important in the business network. And he says he attributes the rise of this paper, or these people attribute, Ansel and Paget attribute the rise of the Medici to these strategic marriage alliances that Cosimo de' Medici created. You can also think about ethnic or friendship and professional networks. So, for example, there's a lot of work by Ray Fisman and his co-authors which look at what happens in Africa in terms of loans and business communities. So they find that keeping everything else constant, South Asian entrepreneurs, particularly Indian entrepreneurs in Africa, tend to have an edge over their African counterparts because they have strong ties within their community, which sort of creates social capital, and that enables them access to more credit relative to African entrepreneurs. So if you compare those with a stronger ethnic network versus those who have a weaker ethnic network and similar professional networks, you find that it makes a difference. You could, of course, belong to two different communities, and you could study how these things affect each other. So you could be a member of LinkedIn, and also at the same time, you could be a member of Virginia Tech or a Virginia Tech alumni, and then look at the relationship between these two and how that plays out in your career or job market and so on. Okay. Of course, you could see whether this one works better or this one works better if you are playing golf in Mar-a-Lago, right? So, all right. So what are we going to look at? We're going to look at a network of pre-existing social connections. We will call this network H. The idea is that this is historically given. So H cannot be altered. This is a given network. And then the network that you will form, as in the networks literature, is going to be denoted by G. So you can think of H, for example, being social connections, and G, for instance, being your business ties. Okay, so this is kind of what is the backdrop of this problem. Okay, then we're going to say that there are local complementarities in effort. Okay, between the players that are linked in H and G. The innovation, or the way we tie up these two networks, is the idea that there is going to be some interaction between these two networks. If there is no interaction between these two networks, I could individually analyze network H, individually analyze network G, but we need something to tie them up. So we're going to, for most of this presentation, what I'm going to assume that the interaction across the networks is complementary. And then I have one little bit where I talk about what if interactions across the networks are not complementary, but they are substitutes. Okay, so the idea you want to think about is that if effort you put into H improves or increases your desire to put more effort into G, and vice versa. If they are substitutes, then if you want to put more effort in H, then you want to put less effort in G. That's the idea of substitutes. Okay. So what do we add to the literature? This is a very simple model to study multigraph formation. We can look at what is the implication of path dependence. So depending on the initial network, you can, the given network H, it can affect G. And of course, we are looking at asynchronous network formation. What it does is also, unlike the physics papers, which take preferential attachment as given, we can endogenously create preferential attachment. So it turns out that certain nodes become more and more important, and therefore you can also, as a consequence of this, you can also identify who will occupy key positions. And then finally, at the very end of the paper, we try to sort of create a dynamic framework for this by introducing a very, very simple overlapping generations model. Okay, so obviously I'm not going to be able to go into the details of all of this. I'll give you a flavor of the paper, and then I will talk about the other paper. All right. So in related literature, there's actually a lot of work on this. So there is the idea of multiple activities in one network, right? So to think about the idea that you create one network, but you're doing multiple things with people in these different networks. So one paper, one of the early papers in this is a paper by Pascal Biland and his co-authors, and what they look at is that there are two firms. There are n firms which have one network of collaboration, but they engage with each other in terms of competition in multiple markets. So they have one network, but the activities are on multiple markets, and then these markets are related because of the production cost, which ties them through these economies of scope or economies of scope. Then there's the paper by Chen, Zenu, and Zhou, which looks at the idea that you have one network, but then you can take multiple actions. So this is, you have one network of friends, but you can do different things with these friends. And again, it looks at how the relationship across these types of activities can affect the final outcome. You can also think about networks as an institution and markets as an institution. So this is the Gagnon and Goel paper, which thinks about these two activities as institutions and compares them. When should you go to one institution versus when should you go to the other institution? So you can think that that is also, in some ways, that's also related to this whole idea of multiple networks, because then you have two different networks which are maybe competing as compared to a framework where you have a network and a market as competing institutions. Of course, there's a large literature on multiplex networks. This is mostly outside of economics, physics, biology. There's also a large literature on hypergraphs. And in some ways, we could model what we are doing here as hypergraphs, because the hypergraph idea is that the same set of agents and you have multiple links between the same sets of agents. But if we do that, it's very difficult to keep track of the different activities. So I'm not going to talk about the large literature on multiplex networks or hypergraphs, and you will see why modeling these as two different networks actually gives you better insight than trying to put everything into a hypergraph. Right, so we have n players, and then given to us is the network H, which is importantly, it's undirected. And since this audience is already familiar, this is the set of neighbors of player I. So this is all those people who are directly linked to player I. And this is the degrees of player I. So this is how many people player I is linked to. Walk and chain, again, as these are saying, you can go from one place to another without retracing, so it's both ways. So these are all, terms by now in this group. It's rather, everybody knows, connected. If everybody in the network, it's possible to go from one person in the network to any other person in the network. This is true for everybody, then it's connected. Components, if the network can be broken up into groups. Empty network, the network with no links. Complete network, everybody is connected to everybody else. The K-dominant network is that there is one group of people that's completely connected, and then the other people are not connected. So if we have 8 agents, I can think of a K-dominant network as this is a K-dominant network because these 4 agents are completely connected to each other. The first set of 4 agents are completely connected to each other, and the second set of 4 agents are not connected to each other. Okay, so this is a K-dominant network. Then G plus Ij is adding the link Ij, G minus Ij is removing the link Ij. Regular network, everyone has the same degree. And we want to focus on connected regular networks because that gives us the kind of power retractability we need. So you can think of connected, what is the difference between connected regular networks and regular networks, where I could have one network of agents, of 6 agents, these 2 triangles. This is a regular network of degree 2, but I could also create them in a hexagon, right? And this is also regular network of degree 2, but this is the second one is this is a connected regular network, whereas this is not a connected regular network. So we will rule out these types of networks and focus only on those. Okay. Then I want to define Bonnet centrality. So Bonnet centrality, basically, it's, apart from the definition, the intuitive idea is very clear. It's a measure of importance or influence in the network. So you start from an agent and count all the weighted paths from that agent to everybody else in the network. And these paths, of course, have a decay factor. So the longer they get, the smaller is their weight. So once you add up all the paths for one agent, that's the measure of Bonnet, that's that particular agent's Bonnet centrality, and you do that for all the agents, you get everybody's Bonnet centrality. So the nice part about Bonnet centrality is that once you have the network, you can kind of compute Bonnet centrality without knowing anything else about the game, because it's just a physical computation of the number of paths from any one agent to everybody else, given there is, of course, there is the decay factor. Okay, and the decay factor actually in our application has to satisfy certain conditions, but that's technicalities. All right. The other thing I want to talk about. So on one hand, we talked about certain types of graphs like connected regular graphs. On the other hand, I want to talk about another type of graph, which is, so if you think about connected regular graphs, they're very, very symmetric graphs. Everyone has the same degrees. On the other hand, we want to talk about a large class of asymmetric networks, and this is the idea of a nested split graph. In the nested split graph, you will partition the agents by their degree distribution. So you put agents into groups by the number of links they have, and the intuitive way, so I will not go into the formal definition. I will show you some pictures, and I will show you in terms of the adjacency matrix what it really means. So essentially what we're saying here is that either 2 people are not connected, or they're friends, or they're friends of friends, or they're friends of friends of friends, and so on. That's the idea behind nested split graphs, and it's a wide range of asymmetric networks. All right, so if I take a set of 9 agents, you can get a whole bunch of nested split graphs, right? So if I look at the first one, which is the most common star network, so agents 1 through 8 have 1 degree, whereas agent 9 is connected to everybody else, so they have degree 8. Okay, so these are the 2 degree partitions, P1 and P2. If I look at this next picture over here, again, I have 2 degree partitions. However, now there are 2, so this is a star with 2 centers. So player 8 and player 9 both are centers of the star, right? So that's why we have 2 agents in the degree partition. Okay, they are connected to everybody else. Everybody else is also connected to them, but they're not connected to each other. So for example, there's no link between 6 and 7 or 5 and 6 and so on. Okay, so the difference between here to from the first picture to the second picture is that in the second picture, players like 1 through 7 have a degree 2. Okay? So they're connected to both the centers of the star. Now, if you come to this picture, this is the third picture, you now have 3 degree partitions, because player 9 is connected to these agents who are in the periphery, and they all have a degree 1. Okay, and then player 9 is also connected to 6, 7, 8. Now 6, 7, 8 are players who are also connected to each other. So these guys in some sense form a complete component, but then 9 is connected to the remaining. So and then this is a more complicated version of that. So again, so you realize that just with the same set of agents, we can go from 1 degree partition to from 2 degree partitions to version of 2 degree partitions where the degrees change, to 3 degree partitions, to 4 degree partitions, and so on. Okay, so you can create a wide range of networks using this. So the big thing to keep in mind here is, very intuitively speaking, if I and j are connected and the degree of k is greater than the degree of j, then I and k should be connected in G. And the easiest way to think about the nested split, the idea of a nested split graph, is that it's an upper triangular. The adjacency matrix tends to have the upper triangular structure. Okay? Basically, what it is saying is that the people in the lower degree partitions are not connected to each other. So if we go back to this picture, this is what I was trying to point out, that 1 and 2 are not connected to each other. They are connected to people in the higher degree partitions, but they're not connected to each other. That's the key idea. Okay. So how does the game work? So players take network H as given, okay, and then they make decisions about what links to form, okay, in G. Once that is done, then players choose efforts, and these efforts are chosen both for network G and network H. So there are 2 effort terms. Okay, so in a sense, you can think that the strategy space of players has 3 things: the linking decisions about who they want to link with in network G, and then the 2 effort choice decisions about how much effort to put in when you interact with people in network G, how much effort to put in when you interact with people in network H. So that's basically the set of decisions people are making. And in stage 2, we're going to use Nash equilibrium, standard Nash equilibrium. So keeping everybody else's, of course, given network G and H, keeping everybody else's efforts constant, what is your effort choice? What's your best response? Stage 1 utility is we take stage 2 utility and subtract. So there is a cost of link formation C. Each link has a cost C. Subtract from it the cost of link formation. So suppose you make 5 links, then each link costs C. So your total link cost will be 5 times C. So you take your stage 2 utility, this is the utility from stage 2, and subtract from it the cost of link formation. That's the idea. What is the notion of equilibrium? We use something called the pairwise stable equilibrium, and this is a mix of ideas from Jackson-Walensky and Nash. So you can think of this as, in terms of link deletion, no player has an incentive to delete any subset of our links, whereas if players are considering forming a link, then they need mutual consent. Which means both of them have to incur the cost of link formation. Another way to think about this is that we want to argue, another way you can think about this is a refinement of Nash equilibrium, which imposes a mutual consent condition on this. So we can think about Nash equilibria where there does not exist a set of 2 players that want to engage in costly link formation. Okay, so that's how you can think about pairwise stable equilibrium. And so this is an idea, I think, that was put forth by Goel Joshi in 2006. I think Sumit is around on the talk. Okay, so now we want to go to the problem of modeling this 2-stage game. And so Xi is your effort, okay, in network G, and Yi is your effort in network H. Okay, so the first term, so let's say this is your effort for network G, and this is your effort for network H. Okay, so this term obviously is the standard concavity in effort that you will recognize from any principal agent type problem. This is the part of the local complementarity. So this is a coefficient which is positive, right? Now Xi is your effort. This is an indicator function. Gij is an indicator function which takes value 0 or 1. If you don't have a link with somebody, then it takes a value 0. If you have a link with somebody, it takes the value 1. Then you multiply it by the effort of another person. So if you are linked to one person in network G, then your effort will be, so if you're linked to J, then your effort, so then the utility you get from this term is lambda times Xi times Xj, okay? And of course, then we sum up over all the individuals to get the total utility. You do the same thing in network H. The key term here is this one, and this is what links the 2 networks together. So my own effort in the 2 networks is also complementary. If gamma is positive, if gamma is negative, then my own effort in the 2 networks is substitutes. Okay, so this is substitutes case. So I'm going to first, for most of the time, I'm going to be talking about the situation where gamma is positive. Okay, so I will be focusing mostly on this case. Is there a question?
Sudipta sir, yeah. Sarvesh this side. So if the story here is that the benefits of connecting in G, I will inherent those from connection in H. Somehow they are related, right?
I will put more effort if you have more directly. I mean, the marginal benefit of the complementarity may depend actually on how many other parts you have in the other network. So that's my first question. And the second question is, it's more a robustness question. It's, do you really need to go through efforts, or could you write a reduced form utility which will only depend on G and H, more general, with some general properties on G and H, and study pairwise stability or pairwise Nash stability with a general utility function at a more abstract and more general level?
Okay, so I will try to go through one by one. So Sarvesh, basically, if you look at the Ballista-Calver-Mengel-Zenu paper, they show that in fact effort is proportional to Bonnet-Sit centrality. Okay, so that's the beauty of that paper. That's what they're saying. So when you connect to somebody, because the Bonnet-Sit centrality takes under complementarity, of course, this is very important, right? So under complementarity, it takes all the connections into account because of the paths. So that's the key result of that paper. Okay.
Okay. So
Nash equilibrium
implicitly, in the sense, it is capturing that.
Okay. So Francis, coming to your question, so in some sense, that part that you're talking about effort, so the complementarity of my actions with that of others is taken into account in each of these terms. But what we're saying is that my own incentive to put effort into the two networks also depends on whether my effort in the two networks is complementary or substitutes. So this is a little bit like saying, you know, if I put more effort into my church group, then it also pays off in the professional network and so on. But yes, your point about whether whether my efforts are complementary with people within the network, that's already captured here. So that lambda and psi are capturing that individual complementarity with other people in the network. The issue is if I want to take other terms, so then it becomes a question of who do I want to make my complementarity with? So if I, for instance, say it's complementary to everybody else's links everybody else's efforts in the network, then of course our results are actually even stronger. So that goes through. The problem will be if I say that my effort is complementary with some people and substitutable with some others at the same time in trying to create a term like this. So as long as we can keep the direction of the results one way, or the direction of how these efforts are tied together in one way or another, things go through. But you know, if I have different relationships with different people, then it's very hard to keep track of the number of paths, which ones are positive. If you know, as you know, the calculations, you know, sometimes you're going positives, and then if it's a substitute, then you have to deduct them. Then it becomes very complicated unless you impose a lot of structure on the network to be able to say something. And then coming back to the question of, can I do this with, so instead of having a two-stage game, can I do this with something else? So in principle, yes. The question is, what are you going to substitute? What network parameter are you going to substitute? And in some ways, we try to do that in the second paper, where we basically say the reduced form is going to be a function of the degrees. So that's kind of where we try to go. I'm not sure what other network parameters I could think about. I guess we could think about the size of my friendship set or something like that. So we use degrees as a simple first order indicator. I'm not sure if I answered your questions.
You did, go on. Junjie may have other questions too. Beware of Junjie.
Yeah, I'm just well, just one quick comment.
Yes.
I think in the paper with Eve and the Chen in the Asian macro paper, we do consider other enrichment of this pair of specifications. We allow some interaction between xi and yj, for instance. So that's certainly allowed in the model extension of the model, but in terms of trackability, is a mess. So even I think even within this framework, if you allow different G and H, allow different lambda to C, I think it's not very trackable, I would say. So I guess, yeah, have to compromise,
so actually,
make a balance.
Yeah, Junji, you're absolutely right. Actually, this came up already with us. So referees had raised this question. The issue here that becomes important is which yj do I choose? Because I have the network. And so then it becomes a question of which yj. If I take everybody, then if it's complementarity, the results become stronger. Otherwise, I have to say something like, okay, I pick the lowest yj, or I pick the highest yj, or something like that. And then it becomes kind of a robustness check. So part of the problem is that who is the other player I pick? Whose effort do I pick to use that? So that becomes another issue. So we try to think about other ways to do this, but there's no easy solution unless you pick extreme, something like the lowest or the highest and something like that. But yeah, yes, I know you've tried that, and we also have to deal with that, those issues. All right, I'll move on. So I'm just going to show you the first order conditions. The only reason I want to show you the first order conditions is that you will immediately see that there is this synthetic matrix that comes up, L, or a composite matrix, whatever you want to call it. And L is not a real matrix, but it is made up of terms from G and terms from H. And then you can see the optimal effort in X is proportional to the Bonnet centrality in L and some weighted alpha H, so some weighted parameter. And similarly, the optimal effort in Y is a function of H and some weighted parameter beta L. Okay, so where beta L is given by this. So clearly, you can now see that the optimal efforts in the two matrices are connected. Okay, and actually under strategic complementarity, studying optimal effort is not the most interesting question because the effort choices seem to reinforce each other and push them in the same direction. Actually, when you have substitutes, the effort choices will go in the opposing directions. So under complementarities, it's more interesting to look at the network formation. Under substitutes, it's looking at the effort choice is an interesting problem, but then again, substitutes are very hard to talk about, very hard to look at. Okay, right. So to show existence of equilibrium, there's a simple idea that given complementarities, the denser networks tend to give you higher utility. So there is no utility from deleting a link. So given that, you can show that we have a improving path kind of process at the back of all this, which drives the proofs. So using that, we can show that an equilibrium will always exist in a finite number of steps. You will converge and an equilibrium will always exist. We also, in some sense, this is what drives the preferential attachment. So those who have high centrality in H are always beneficial agents to link to. Okay, and of course, so yeah, so that's kind of the outline of what drives the existence result. So now I'm going to talk about the key result of the paper. So what we do in the key result, or this main result basically says, look, I have to start with H and talk about G, but I cannot assume that H is anything. So I want to impose certain conditions on H. So in order to do that, we say H is one possibility that H is a nested split graph. So that's a wide range of asymmetric networks. The other one is that H is a connected regular network. So the difference between the two is that this is very asymmetric, right? And this is very symmetric. Okay. And we want to look at network formation in these two situations. So the second one is very easy. So suppose H is a connected regular network. So everyone has the same Bonnet centrality. So everyone's equally attractive. So then everything is driven by cost of link formation. If the cost of link formation are very high, you have an empty network. If the cost of link formation are low, if it's worthwhile connecting to one person, since everybody is equally important or equally influential in this network, you're willing to connect to everybody. So immediately you go to the complete network. So it's very easy to see what's going on. So now let's see what happens if H is an NSG, and then I will go through the steps. Again, with NSG, this part is easy to understand, right? So either the complete or empty have to do with the cost of link formation. If the cost of link formation is very high, then the network formation will not happen. If the cost of link formation is zero, the network formation happens. But if cost of link formation is somewhere in between, what you will get is that if H is an NSG, then G is also an NSG with at most one non-singleton NSG in it. Okay. Now let's see what can we say about this non-singleton NSG component. So first I'm going to say that G has n degrees, okay, and H has m degrees. And so this is the degree partition of G and the degree partition of H. So first result is that those in the highest degree partition of H will be in the highest degree partition of G. Okay. However, it is possible, based on the cost of link formation, that other people, or for say somebody in partition, or not somebody, degree partition m-1 of H also belongs to degree partition. So what we're saying is that if you are in the highest degree partition of H, you would certainly in the highest degree partition of G, but people from other degree partitions may also get there. In that sense, G induces a coarser degree partition of H. Now
can I just ask one clarification regarding the
sure.
So in case someone from m-1 is part of n in G, then is it only some agents can do, or then all of them will be the part of that? All of them, right?
So,
yes.
so I will come to that.
If it's optimal for one, then the
so
same goes through, right? Right. Mm-hmm.
So people in one degree
At the same payoff,
right, will behave.
Thanks.
Okay. So now let's come to the people in the lowest degree partition. If you're in the lowest degree partition of H, okay, then if you're in the lowest degree partition of H, you will be in the lowest degree partition of G. Okay. But again, it's possible based on the link formation cost that G induces a coarser partition of H. So I'll show a picture in a minute and you can see how this works out. Now, this is to answer Sarvesh's question, which is what we call the non-partial overlap property. So let's look at everybody in the in-between partition. So two players who are equally central in H cannot have different degrees in G. So if you belong to the same degree partition in H, you cannot be in different degree partitions in G. Of course, it is possible that people with different degree partitions or different centralities in H belong to the same degree partition in G, which is the idea that G induces a coarser partition of H. So if you look at the picture, so suppose this is my H, okay? Then I can have G based on the cost of link formation, which is exactly identical to H, that's this one. Or if the cost of link formation are high, then G will lose some links. So this is G, this is one possibility. Or if the cost of link formation are low, this is another possibility. So this is what we call coarsening at the top, this is what we call coarsening at the bottom, and this is the identical structure, right? So if you look at what I was saying, the G will always induce a coarser partition. G may induce a coarser partition of H. That's what happens. You can get these types of outcomes depending on the cost of link formation. All right. So to sum up, what this is saying is that there is a silver spoon effect. So if you are in the highest degree partition in the formed network, in the inherited network, you continue to be in the highest degree partition of the formed network. There is a silver lining, which is G is coarser than H. So depending on the cost of link formation, it is possible that there is some movement from of the degree partitions. And the other thing that comes up is that G is always a coarser partition than H. So depending on what H you're starting with, it's easier to pin down the degree partition. Sometimes you can pin it down exactly, but in general, we know that G will have fewer degree partitions. And then, of course, I already explained the second part of the main result, which is if the inherited network is symmetric, everybody is equally important, then the formed network is also symmetric. You could also ask that, so, what do I really care about this in the sense that everything that we have discussed till now is about degree partitions and it is not about utility. So can you say something about the relationship between these things, okay? So suppose, and the key issue here is for somehow to put a bound on when two people form a link, it obviously affects everybody else's utilities. So the key point here is to somehow be able to put a bound on that. So suppose I consider this term U upper bar. U upper bar is basically the last link in the network. Suppose H is a complete network, G is one link short of being complete. You add this link, the utility that generates is U upper bar. Similarly, U lower bar is the first link. So H is empty, G is empty, you add the first link. The utility it generates minus the cost of that, right? If U upper bar is greater than U lower bar, these will go through for utilities. Okay, so under this set of sufficient conditions, everything that we can say about the degrees also holds for utilities. All right. If I want to explore substitutes, basically that term gamma, which is the I mean, we talk about substitutability within the own network and so on, but essentially I'm going to say that my own effort across the two networks are now substitutes. What do we find? Suppose this is my H, then depending on the cost of link formation, you can have empty, you can have complete, because under substitutes, a lot of things are possible. You can also have something like this, like a core periphery. The interesting one is this, which is the inverted four dominant group. So if you observe here, agents 1, 2, 3, 4 are completely connected. 5, 6, 7, 8 don't have a connection. In this network, okay, which is G, if this was H, G, it's flipped. So 5, 6, 7, 8 are completely connected, and 1, 2, 3, 4 don't form any links. So this is like, we call it Bertie-Wooster equilibrium. So this is the rich guys or these are the people who had no social who did not have any social connections, so they formed a professional network. These guys had very strong social connections, so they choose to put all their effort into their social connections in this network, choosing not to do anything here because effort across the two networks are substitutes. So they put all their effort here. Since they're substitutes, if any effort they put into this network actually reduces utility, knowing that it is costly to form links, no links are formed. So 1, 2, 3, 4 stay isolated in the second network, 5, 6, 7, 8 form a completely connected component. So we're just saying that these are possibilities that can arise when I'm looking at substitutes. All right. Then we also do an OLG model, and wow, I'm running out of time. Okay. We also do an OLG and show that, same kinds of results will hold. So we are now actually working on a more general OLG model where we have human capital formation. So this was a very stylized OLG model. We now have that, and we also have the idea that there is maybe favoritism from the parental generation to the children's generation. And then we also are looking at what happens if both of these, so human capital, so in one case we look at purely human capital formation. In the second case, we look at these parental connections and their importance, sort of favoritism type idea. And then we also look at what happens if you have a mixture of both going on. All right, so now we want to look at formation of multi-relational networks under different conditions. Okay. So we want to look at the formation of both networks at the same time, and we focus on the degrees of players in the networks as the element that determine their payoffs. Right. So again, we are not going to focus on directed networks. We're going to focus on undirected network. A network is a set of players and the edges or the links. Then the multi-relational network, M, is composed of two different networks. Links are formed by mutual consent, okay? And the idea here is that we wanted to think of a network as like a production function. So going back to basic, basic consumer theory or production theory. So imagine a utility function where the inputs are the degrees in network 1 and degrees in network 2, and then that generates your output or payoff. Okay, so the strategy profile for the two players is the strategy profiles are a set of linking decisions for every player in network G, set of linking decisions for every player in network H, and then that gives us the multi-relational network M. The definitions of these things I've already done the same. They are the same. Here, of course, we have to remind ourselves that this can be true for G, H, or both, right? So if it is true for both, then we say that M has that property. Otherwise, it's possible that G is complete, but H is empty. Okay, so if I want to say M is complete, it means both G and H are complete. The relationship to the literature, well, there is the sort of the starting point for this probably is the Goel and Joshi paper, Unequal Connections, which looks at degrees. There is, of course, the multiple activities paper I already discussed, the two multiple activity papers. The first paper that I just discussed right now. There is multiple network formation has been studied in some way. So there's the Jackson-Ney paper in PNAS, which looks at trade and conflict. So the model is rather simple. And there they look at, they have data to look at conflict and trade. And the argument is that actually, if I remember correctly, trade reduces conflict. And then there is this other paper where most of it is on multiple activities, but there's a small section at the end where firms are forming links on multiple networks. What this paper is missing is the spillovers of the links for, so if I and J are connected, then in one network, it does not have spillover effects on other players, except in a very indirect sense. It's mostly how it affects I and J. So this is a multi-market competition paper where players can sort of steal secrets or market share from each other on both markets. So each link denotes how much. These are this is an imperfect competition situation or differentiated product situation. And so if a link between I and J exists, it tells you how much market share you're going to be able to steal from the other firm and so on. Okay. So now the equilibrium concept obviously is a modification of the pairwise equilibrium. So it has to be a Nash equilibrium, but now the mutual consent condition has to hold for both networks. Okay? So just like before, we need mutual consent for a link to be formed, and now we need it to be true for both networks. So the payoff function, as I said, is very simple. My payoff depends on the number of links I have in network G, and then the number of links I have in network H. And you could argue, well, then how is this really strategic? Because link formation requires mutual consent, even though my payoffs are just a function of my degrees in both networks, in the end, because the mutual consent requirement, it ends up being a strategic problem. So you have to, because you only have a degree if the other player agrees to accept you in their network. Yeah? So example, you can have a bunch of firms that set up different types of collaboration links. You can have R&D in different areas, or you can have plant sharing and R&D. So it's just building on the same type of work that Goel and Joshi and Francis have done. So you can have this type of R&D, and then in the second stage, you can have could-no competition. So we have some examples in the paper, but this is one easy way to think about it, which relates to the earlier literature. We can, now, of course, one thing you have to remember here is that not all links are possible. So if these degrees are admissible, and then K is the number of new links you want to form, if this is admissible, then the marginal payoff is defined as the difference between adding these links and network without the links. Similarly, you can define the second order marginal condition by looking at what will happen between this network and this network. Okay. You can again define the same kind of ideas for network H. Why are these important? These are important because I can define strict concavity and strict convexity using these, right? So the network is strictly convex if these two are satisfied. it's strictly concave if the opposite holds. And now if I am going to look at these types of terms, then I can use it to define supermodularity and submodularity, which I will not talk about, but these are also things we explored in the paper. So the cross partials, so to speak, can be used to look at these types of ideas. And so what's the main idea? Suppose the pair function is given by what we said, and the network satisfies strict convexity. Well, under strict convexity, you can easily show, because forming links is beneficial. You can easily show that there will be a pairwise equilibrium which will always exist, and both G and H are K-dominant networks. Essentially, if you go back to the idea of what determines the size of the K-dominant network, it is the cost of link formation. So once you think about the cost of link formation, it turns out networks. However, the important thing to keep in mind when you look at this is that G and H need not be the same network. So M need not be K-dominant. G and H can be K-dominant, but M need not be K-dominant. So we have some examples that are like this. Okay. So this is G, but H can be this. Or you can have something like this. In G, you can have those two players having a link. In H, you can have those two players having a link. Okay? So depending on the cost of link formation, you can have this, which basically tells us that yes, G and H are K-dominant. However, M need not be K-dominant. It need not be exactly the same network. Okay?
Can I ask one? If the cost of forming the link is same for G and H, then is it always that at least there exists an equilibrium where the structure of G and H is same?
Okay, we assume that the cost of link formation is the same anyway. We haven't looked at we haven't allowed for different costs of link formation.
Okay.
So the question is it always true that there is one structure that is exactly identical? So if I take the same set of agents,
so accented, they are all symmetric, right?
Yeah, so I mean, so at some level, the intuitive idea is very simple, right? If C is infinity, both G and H will be
absolutely.
Right? So the question is, for every C, does this happen? That I am not sure. But does there exist a C where this will happen, given the same set of players and the same parameters? That is true. But for every...
So say the examples you have drawn, the one on the left where G is completely connected and H is empty. So if the cost is same, then there could also exist like in the sense inverse image and then somewhere in the between also. So maybe it's a...
Yes. Right. It depends on the benefits, right? So, I mean, so in the paper, we actually have a table of benefits that will show you how to generate these networks. But it also depends, I mean, at the end of the day, this is a combination of this one, right? And the other one. So, yes. So now, we also look at what we call, so, the first model that I'm talking about, you could argue is very simplistic, right? Because it does not have anything about the other players. So we look at a model where we have the first model, right? So we have this. So, and then we introduce a second model which we call the playing the field model. And there, what we do is we say, well, it's a function of your degrees plus your degrees and your degrees in G, and everybody else's degrees in G. Okay. And then we can vary this term to see how much this element, which we call playing the field element. This is the sum of everybody else's links in network G. This is the sum of everybody else's links in network H. How that matters, okay? So by varying T, we can vary the importance of this and then look at how the links of other players matter in the network. Now, again, if we assume strict convexity, things are very easy. And G and H will be K dominant. They will tend to have the same kind of issues. If we give up strict convexity and go to the world of strict concavity, then the cross partials start to matter. So then whether we impose supermodularity or submodularity, under what conditions, that becomes very difficult. In fact, it's not always easy to give a clear characterization of what will happen. We can, most of the times, we can talk about properties of the equilibrium. It is equilibrium networks. It is very hard to characterize the equilibrium network. So we're kind of working on that. Hopefully, maybe by the middle of next month, we will have a draft ready. And that's where we stand. So I want to say that, as everybody knows, probably for the first paper I mentioned, Sumit and Saber are my co-authors. And on the second paper, we are all working on this together. So these are my partners in crime. And I think I have managed to finish just on time.
Yes, you actually have like 8 minutes remaining.
Really? Are you sure? Because according to my clock, I have 2 minutes, but okay.
No, I mean, you can talk a bit more because
no, yeah, it's fine. It's fine.
yeah.
So I am happy to take questions, but I want to say that this degrees model is actually quite complicated once you start to look at these cross partials. There are many things that can happen. Just like we said, I mean, under substitutes, under strategic substitutes, all kinds of problems arise. So if I impose the concavity, then these things happen. And so later what we try to do to simplify things, we also see if I just focus on people that are common to both networks. So if I can try to change the utility function to think about, it depends on my connections and also only on the people that are common to both networks, that helps a little bit. But in general, it's, yeah, this is a fairly complicated problem. And of course, as you realize, because all these are discrete connections, so one cannot use standard techniques. Everything has to be played around using these discrete techniques. So that's the two models that I promised.
I have one question actually, but I appreciate how complicated it is, even if you only pay attention to degrees, actually, to write down the utility functions in the second model. But I'm coming back to the application then, and I'm wondering, those applications about, let's say, family networks and business networks, or ethnic networks and business networks, would it make any sense to try to write a more structured model and think, because it seems that actually more is going on than just the degree, actually, that you care also about the fact that, let's say, the people that you're connected to in the same are themselves connected to either the same or direct or different agents in the two networks. So either you have support networks or you have networks which allow you to get weak link connections. So it seems that some super interesting things may happen in more structured models, something which, now I'm stepping back from what I said before, maybe you want to be less general, but construct something which would be a nice application with a story behind it. So have you thought about it along those lines?
Okay, so now Francis, on one hand, you want me to go in one direction, now you're pushing me in the other. Okay, so
I'm like two referees at once, you see.
There are two different models, so you have the freedom, you can do that.
You have two activities at the same time.
So, okay, so I agree that these two models are presenting different flavors. In the other one, we can be more focused on certain things. This one, we go back to a very basic network characteristic. But the one part that we're currently exploring this, Francis, and this is the only part that kind of goes towards the story you're talking about. What if I identify agents with whom I have links in both networks as being sort of the key drivers of my utility? So that's one that we're doing. So that still allows us to stay within the framework of degrees and talk about the importance of people with whom I have common connections. But to do what you're saying would somehow require us probably to think about giving up degrees and maybe even talk about groups of people I'm connected to or something like. I'm not quite sure how we would write down a reduced form model that uses some other network characteristic. I mean, I agree that degrees are very reduced, which is why we also introduced the playing the fields model, which is on one hand, I have only my own degrees, and the only way the game happens is because I need permission from others. On the other hand, I said, okay, all the degrees in the network, which is again the very other extreme. So these are kind of two extremes, which is why we thought, okay, to tell a nicer story, maybe I figure out the number of people that are connected in both networks, and I use that to tell a more nuanced story. So Christoph might be I don't know if Christoph is here. I know he was on vacation, so he had said that he might chime in. I don't know if Christoph is here. I don't know if Sumit is here. If anybody else wants to say anything.
Christoph didn't join today.
Hi, actually, I am here. So hi. But I have to actually leave. I have to actually go to another one because Kaushik Basu is speaking today on morality and game theory. So his session starts at 10. So, but I think, Francis, that's a great point. And I think that I think we need something where something very specific in one network, which captures the sense of kinship, identity, etc., and how it relates to outcomes in the other. I think would be something great to check out. Absolutely, I think it's a great suggestion. Yeah. So yeah, I hope that came through.
Yeah.
Yeah. So definitely.
Enjoy your other talk.
Yeah. Thanks. I'll see everybody. Bye.
Yes. So I think the next speaker is somebody from electrical engineering. So that should be an interesting perspective as well. I just wanted everyone to know that. This is Tamar Basser from Urbana-Champaign.
Yeah, so we'll send the invitation pretty soon.